All right, so let's get your notes out as far as review stuff. This is the same thing we had up a couple days ago. I think it was on Thursday we wrote this stuff out. So I'm going to add to it just a little bit here. So again, we'll get a little bit of review in since we're short, cut a little bit tomorrow here, and go over the homework problems. And just kind of remind ourselves where it is we're at. And even the new stuff, to be honest, that we're going to go into is somewhat related to the things we're doing. And the homework I give you, which is some new stuff, is still like doing chart, local max min, I mean, that kind of thing. We're just going to do it with some different functions. So it really won't be that, hopefully shouldn't be that confusing anyway. So where we started here in section 1, so what are some of the things you need to be able to do on the quiz? Well, something like this, give you a function, find f prime of 2, and be able to work it out the long way. And we'll do an example of that tomorrow. But, when we did it back in section 1, we could do this limit the long way using algebra. Remember what happened? You foiled it all out and stuff the h's canceled, and you found it, that we called that the long way. Since we've been doing our calculator limits, though, we could actually do this same problem and let's use your calculator. I could tell you to set up your limit. Here's a function, find f prime of 2, and then set up that function. For example, let's say we didn't know, we don't know the derivative of tangent, right? We haven't learned that one yet. Now, actually, in about an hour, by an hour from now, we will know. But let's say I just gave you f of x equals tangent x, and I ask you to do f prime of 2, right? Using the definition. So you would set it up. What would it look like? Well, it'd be the limit as h approaches 0 of what? F of, we just put a 2 right there, right? And a 2 right there, so it'd be f of 2 plus h minus f of 2 all over h, right? Now, we'll go through one of these tomorrow, so you don't have to necessarily write this down. So this would be tangent 2 plus h minus tangent 2, right, all over h. Now, is there any algebra you can do to that? You can't distribute a tangent, right, just so you know, right? You distribute multiplication. This is a multiplication. So there'd be nothing to do the long way. There'd be no algebra work here. So you go to your calculator and type this in. Right? Right? Just what you did on the worksheet today. Right? The one that said limits and derivatives, you had these limit problems, right? They had h's in them. But you didn't type in h's on your calculator, right? You used x, right? So you do the same thing. You'd set it up, you'd type this into your calculator, right? That's what you're doing on that backside. So you would type this thing in right here, except you'd use x's instead of h's. You'd look at the table, right? And you would see what the limit is, and that would be the slope of the tangent graph at 2. Correct? I mean, so that would just take what we were doing here, when we were doing it out with algebra, the long way, when we first were doing it, and it would just apply it to the same thing. We would just take a function that we don't know what the derivative is, and we would say, let's just set up the limit using the definition of the derivative. And now, instead of going down and doing algebra, since there's no algebra we could really do, we'll just type that in our calculator, and we'll look at what it is there and get the answer that way. Okay? So that's nothing more than applying this to what your worksheets have been doing. You had the one worksheet that had a bunch of algebra limits where you did the factoring and cancel, common denominator and cancel, conjugate and cancel. But then we also had the worksheet where we did some of these limits where we just put them in our calculator and did the table. Okay? So we want to be able to do that, both for limits that are a derivative, like this one, and for limits that are just plain old limit problems. All right. Then, of course, we learned our shortcut, and so we want to be able to do those, and we can practice some of those tomorrow. Then we spent a lot of time just looking at limits. Now, we just talked about the whole, factor, common denominator. That's that worksheet that we did, so we need to be able to go through and practice some of those and be able to do that algebra. Calculator tables, we've been doing that on these 2 worksheets, so hopefully we're good with doing that. And then just looking at a graph, like those piecewise graphs, do the cars meet, and, that kind of stuff, just basic basic limit stuff. All right, and then like number 20 we had today? 21. It's 21 on today's homework. It was 20. 20. With doing the whole chart business and local max min, doing the number line, the F prime number line, be able to do that kind of stuff. That's a big, that's a pretty good summary. The only thing missing off of that would be the continuous function stuff, and we've got some problems to deal with there. And the whole thing we did the other day. Well, let's see. Let me pull that from our notes. Let me pull that from my notes on Friday. So on Friday, of course, here was our table. Here's our table example we did. Here was number 21. And then this stuff here, right? The function is continuous if it's defined at A, so it can't have, an undefined spot. The limit must exist, so there can't be a break, a place where the cars don't meet. And the limit has to equal the output. So it has to have an output, which this one does. It has to have a limit, which this one does. The cars meet right there, but they're not the same. So all of these would be examples of discontinuous, right? That's what these examples are over here. Here's what has to happen for it to be continuous. These would be examples over here that violate these things here, okay? And so that's the other part of it. And then we also talked about what it takes to be a differentiable function. And these are all posted on the website, these notes, everything's up there. A differentiable function is continuous, and F prime and F prime exists everywhere, right? F prime exists everywhere. So these would not be differentiable. These would be continuous, right? You don't have to lift your pencil. There's no holes or breaks or gaps or anything, but they do have sharp point or a vertical tangent. So they're not differentiable. So a differentiable function is continuous, and the derivative has to exist everywhere. So that was, okay. Oh yeah, and then we did talk about the antiderivative thing. We did talk about going backwards. I don't think that's going to be on the quiz where we have to do that power with that working backwards thing. That'll probably be on our next one. We probably won't. But the whole idea of an antiderivative could be on, and we'll talk about that some. Okay, so there we go. That's where we're at. So that's pretty much the stuff for the quiz. So short of just practicing sometimes, giving you a chance to practice a few things, that's what we'll spend some time on. Yeah. Under 2.4, I'll be honest, I'm not even sure. I think that was actually in 2.3, but it doesn't matter. I think in the book, I think that was on page 106, so it was actually in section 2.3. The idea of continuous functions and differentiable functions. 2.4, about all we really did was that idea of antiderivative and that idea of, and the main one is the chart, the whole chart problem, like number 20 we have to do. Okay, where do you want to start with looking at the homework here? 52 and 54 will be good ones. Those are really the chart kind of thing. And I said, here I said that let's hold off on those, but we will definitely do those. Was 66, 67, those were in, let's do one of those, okay, like 66. Because they're basically the same. They ask it a little differently, but 66 and 67 are basically the same. And these are really good problems. Matter of fact, I was going back and looking at some of our practice tests that we do as we get ready for the midterm and we get ready for the final. And these are always in there, always, these piecewise functions. So if we take a look at 66, it says the function is what? AX plus 1, x is less than 2, x squared, that's it, if x is greater than or equal to 2. So the idea here is that, and they always ask, there's two types of questions that they ask with you. One type of question is it, what will make it continuous? What value of A will make this continuous? And the other question is, what value will make it differentiable? Okay? Well, so we got to think about what's happening here. Well, what's happening at 2? Well, we have a line that's coming in here. It doesn't really matter what it looks like at this point. We got a line that comes in here at 2. I have no idea if this is what the line looks like. I don't care right now. But we have a line that comes in at 2, but doesn't include 2. And then we have a parabola that takes off from there. Right? Which could, I don't know. I know that's not it. But you know what I mean? So if it does that, is this continuous? No. What would make it be continuous? This and this would have to be together, right? To be continuous, you can't have that gap there. So those two y values have to be the same. So how do we do that? Well, right. And so the question is, so what, on 66, what's it say? It says, find the value of A for which the limit exists. Okay, that's a different question. Okay, that's saying for the limit exists. Okay, so forget continuous for a minute, but you'll see it's the same question. For the limit to exist, what has to happen? Those two red dots have to be at the same y value, right? It's the same thing. You can't have this gap for the limit to exist because the cars wouldn't meet. So we need those to be together. Now, if the question was for it to be continuous, it'd be the same thing, right? Those two red points have to have the same y value. So it's going to depend on A. So there's one A value that will make that happen. Every other A value will make there be a gap there. Okay? So how do we do it? Set them equal to each other. There's one more piece to it. Involves the 2. With a 2 in for x, right? Because we're talking about when x is 2. So we need to plug a 2 in for x. Then the line will be this. And the parabola will be that, right? And they have to be equal, means their outputs have to be the same. So 2a has to equal 3, a has to equal 3 halves or 1.5, and that's how you solve it. So the same thing in 67, except 67 asks a different question. 67 says, suppose f is continuous at 2, find the value of a. So you see what I mean? To be continuous, where the one stops, the other one has to leave off from that same y value. So again, they have to have the same y value. So you put a 2 in for the x, where the break is, and then you make them equal to each other. So every problem like that, that's what you do. Okay, then part B, in both of them, is the same. In 67, it says, is f differentiable? In B, it says, find the value. If A has that value, does f prime of 2 exist? See how that's the same question? Does f prime of 2 exist is like saying, is it differentiable? Okay, well, to be differentiable now, so what we've done is we've said, okay, if A is 3 halves, now when this line ends and the parabola takes off, we got this. The way I drew it here, does a derivative exist? The way I drew it right there in red, does a derivative exist? No, why not? It's a sharp point. Right, it doesn't have to be a V, but any sudden change in direction is a sharp point. So the derivative does not exist. The only way for one graph to stop and another graph to take off with the same, like a parabola, they have to have the same slope at that point. So we got two different questions. So the one for continuous, are they continuous? They have to have the same y value when x is 2. To be differentiable, they have to have the same slope when x is 2. And then it'll be smooth. And that's what we mean when we say differentiable, smooth. No sharp, sudden change. So what we need to do is do the derivative of each of these. We need to do f prime of each of those. And then plug in a 2. And then those have to be equal. So what's the derivative of ax plus 1? Well, that's weird. We haven't seen something like that. Remember, a is just a number. So what's the derivative of ax? You bring a 1 down in front, that drops to a 0. It's just a. Well, what's the derivative of 3x? What's the derivative of 3x? 3. Derivative of 4x? 4. Derivative of 5x? 5, right? Derivative of ax is a. Okay. And the derivative of 1, of course, is just 0. So the derivative of ax is a. And what's the derivative of of x squared? 2x. But then we have to plug a 2 in. So we get 4. So a would have to equal 4. What did a equal? 3/2. So did that value of a make that work? No. Now, because a lot of times the problem is find a so that they're differentiable. So that's how we work it. We get a is 4. This one, they said, does that value of a make it happen? So I guess we could have plugged 3/2 in here. We could have plugged 3/2 in here for x. So we could have said, okay, this is 3/2 x plus 1. Now do the derivative. That's 3/2. Okay, now they do the derivative of this one, 2x. Put a 2 in, we get 4. Does 3/2 equal 4? No. No. So it doesn't make it work. Their derivatives are not the same. Their slopes are not the same. Okay, this one, the line would have a slope of 3/2, and the parabola would have a slope of 4 when it took off. So it would be a kind of a sharp point. Okay, let me see. I should have looked this up, but I had some people in here this morning, which is awesome. So I didn't quite get a chance to look this up. So I'll bet anything. What's that? This search? I do quite a bit. I got so much stuff stored in here. All right, let's. This is one of our practice exams that we use when we're. It's the length of the actual AP test. We could do some of these already. Looks like it, yeah. 36, it's actually 36 pages. In a book with like 4 or 5 exams, so this is actually 36. But it's only got a couple problems per page. There's 45 multiple choice questions and 6 free response questions on the actual test. Oh. No, that's not it. Oh, here's one. No, that's not. Some of these problems look similar to one.
They're just way
well, we're just missing a few things. How about this one? No. Not yet. Someday. Running out of room. Running out of time. Hey, we do this problem. We'll come back to it. Oh, shoot. Oh, we could do this one too. We could do this one. Limit as x approaches b of this right here. You try to plug in a b. Square root of b minus square root of b is 0. B minus b is 0. 0 divided by 0.
Keep going.
0. Keep going. So what would we do? This is no calculator part right here. Conjugate and cancel. So this would be root x plus root b. Root x plus root b. Okay? Conjugate and cancel. On top, we would not do anything. We would just leave those. What would you get on the bottom? This very question could easily be on the, who is this with me? On the bottom, we get x minus b. Can you cancel those?
No.
Almost. Just like that 9 minus x one we did. Take out a negative, would turn that into that. Now we can cancel. now as x approaches b. So square root of b plus square root of b is 2 square root of b with a negative. That's what I said. Okay? Conjugate and cancel. Just, okay? So that could be one. And then right here, the graph of a function whose domain is the closed interval shown above, which of the following statements about f is true? The limit as x approaches 3 is equal to 1. X approaches 3, what is the limit? 3. The cars would meet up there at 3. So that is false. X approaches 4, the limit is 3. Limit would not exist, right? The cars don't meet. Okay? F is continuous at 3. False. Now I told you that I would, you would have to tell me why it's discontinuous on this quiz. We gave those 3 reasons, right? Which of the 3 makes this not continuous at 3? No, that's differentiable. You're talking about derivatives there. Which one of those 3 makes this not differentiable? Or it's not continuous?
The output is different from the limit.
Output is different than the limit, the third one. F of A must be defined, there must be an output, which there is. The second choice was the limit must exist, which it does. The limit's up here at 3, and those 2 have to be the same. The limit is 3, the output is 1. This is not continuous there. Okay? There's like a gap or a jump. That's the informal way of saying it, but the formal way of saying it is the limit doesn't equal the output. That's why it's not continuous. Is it continuous at 5? Yes. You wouldn't lift your pencil. The output is right there. The limit is the cars meet right there. It fits all 3 of those. It is continuous at 5. That's the
That
choice
question,
right there.
would it not be differentiable
This
at 5?
at 5 would not be differentiable, right? That's a sharp, sudden change. We would say it's not differentiable at that point. That's true. But it is continuous. Okay, and then, of course, we found the one that was true, we think, so it would be choice D. Limit, does a limit as x approaches 6 equal f of 6? That's false. The f of 6 is that point. The limit doesn't exist, right? Because the cars wouldn't meet at 6. So, so they're all false except D, right? So anyway, those are some kind of, just quickly looking at some examples. I was hoping to find one. Maybe we'll have some work time here later. Maybe I can find another one. Oh, this is a good one too. This not one I'll give you right now. I mean, certainly could do, but they give you this. This is no calculator now. This is no calculator. Okay. They give you this function, and they want the slope at 2, f prime at 2. Now, what you'll want to do at this point is you want to do like an f prime formula, right? But geez, we don't have a formula for absolute value. How do you do derivative absolute value? We don't. As a matter of fact, they don't want you to do an f prime value. What should you do here? What's the first way we learned about slopes? No, I'm sorry. What's the first way we learned about derivatives? What in chapter 1, all of our functions were what? I heard it. Graphs. All of our functions were graphs when we first learned about this stuff. This is a problem where you should do a graph. Remember I said these basic functions, we need to know how to graph them? That's what you should do here. You should take this problem and you should say, okay, oh yeah, I know this function. What is it? It's the V graph shifted 2 to the right and up 3. So 2 to the right and up 3, and it's a V. They want f prime of 2. That would be right there. What's the slope? Undefined, non-existent. There is no slope at 2. It's a sharp point. What if they would have asked for f prime of 3? What's the slope on a basic V graph? 1, right? This side's -1, this side's 1. So if they'd asked for f prime of 3, it'd have been 1. See, so we don't need to know any formulas for that. We need to know about our shifting and stuff, okay? So that's exactly that. Those are the kind of questions that they get at, and they want you to be able to do. So we should have thought of that as a shift right 2 and a up 3, and then we answer the question, what's the slope at 2? Oh, doesn't exist. All right. Okay, so that's 66 and 67. Now let's talk about 52 and 54, because those get into this idea of this chart stuff, and you know, like number 20 as well. Very, very basic kind of thing. Now 52 is kind of, and this will be good. This will be good to go through some of this, so we don't maybe have to take as much time going through a max min one tomorrow. You know, I don't know that we'll be able to go through all those things, but we could save one like number 20. We could go through it tomorrow. These are little harder versions of the same thing. Okay, 52 is really a hard one, to be honest with you. This is the one I wanted to throw in there that really make you think, really make push you on this a little bit. But 52 gives you this function that is, what is it? Just basic x cubed plus minus, okay, thank you, 3x squared plus k. And I don't know why I wrote it. Okay? K and 6. Yeah, I do. All right. And it says what values of k will make this have 1 root, or what's it say, x-intercept? 1 root, 2 roots, 3 roots. Okay, this is a great example of a problem where you have to think through what they're asking about. You have to bring a bunch of different knowledge together before you dive into any calculus stuff. First thing I would ask you is picture this function in your head. Picture this function in your head, because this is absolutely a no calculator problem. Sometimes they'll put these in the calculator part, but because of the k, what in the world would you put into your calculator, right? They give you these because your calculator isn't really a whole lot of good to you. Okay? But mostly this should be a no calculator problem. So, what do you picture? Anybody? Chris, what do you picture? You started to draw it in the air. It wouldn't be a W. You're close. It could have 2 humps, right? And the tails would go different directions. When I picture this, it's a cube. Right away, I'm picturing something like this. Now, it might not have 2 humps. It might just go kind of like that, right? But if it's going to have 3 roots, it's going to have to do this, right? Okay? So right away, you should be picturing that. And then ask yourself, well, what's this K? What's that doing? That's a vertical shift. So now I start thinking about roots here, and I start thinking, okay, how could it have 1 root? Well, could do that. Wouldn't that have 1 root? And if I shift it up farther, still just has 1 root. How could it have 2 roots? Shift it down how far? Just enough for that to bounce, right? Just enough for that to bounce. So there's some k value that's going to make that just hit, and then I'll get 2 roots. Now what would make 3 roots? Move it down a little farther. How far? Just far enough until that is bouncing, right? And that's just touching. And then we would have, in between there, we'd have 3. And then what if we shift it past that point? Then you'd be back to 1. So by that, and that wasn't terribly difficult, that whole process. I mean, but you really had to draw on some things that you're not used to having to do that. But that's what. But see, to me, that's given it to you. That's told you now what to do, because the key to it is that point and that point, right? That's the key to it. How far until we go from 1 root to 2 root is when that point is here, and when that point is here. Those are the local max and local mins. The key to this is finding the local max and local mins. Oh, how do we do that? Problem 20. Come on, guys. Yeah, how do we do it? We do the derivative, which would be 3x squared. That's why I was thinking about the 6. minus 6x, and the k would go to 0 because it's a constant. And we do what? We want to know when that equals 0 because that's going to find these two humps here for me. Okay? So what do? We factor out of 3x. I knew this would be hard. I didn't think most of you would get to it, but it's a great discussion. And now the next time we see it, I hope a lot of you would see that. And the next time we see it after that, more of you will see it, right? That's when we do these review packages. It's the same process, right? You're not always gonna see them the first time you go through it. Maybe not the second. Hopefully, whatever. So what do we get? We get x equals 0 and 2. So my picture is not quite right, is it? It's more like this. It's going to be when x is 0 and when x is 2. We know it goes up like so. Okay? So it's going to be this sort of thing. Well, it's going to be kind of this sort of thing where the max is going to be there and the min is going to be over here at 2. Right? Now I could do my whole f prime number line, but I know it's a positive x cubed, so I know it's got to go up and then down. And so I'm not even going to do my number line right now because they didn't ask me for the max and the min. They didn't ask me for that. If this was a local max min problem, we would now put those on a number line, right? Do our whole negative positive thing. So we did in number 19, we did number 20, we did 21 the other day. Okay? So I would do that. But I know enough about x cubes and I know I got this. Okay, so now what I want to have happen is I want to find when this is just touching there. How can I find that? When will this bounce? When will this touch? How would I do that? Remember, this is the F graph I'm drawing. Put 2 in to the F graph. Right? So I get 8. 4 times 12, 3 is 12, 8 minus 12 is negative 4. So negative 4 plus k when I put a 2 in. And I want it to be an output of what? 0. So what's k got to be? So if k is a 4, this will just touch. And I'll have 2 roots. So first question was, when will there be just one root? No. Want to be greater than 4? It's when k is 4, this is just going to touch. To have one root, we need this graph to be shifted above that, right? So it just has one root, like my picture here. So to have one root, we need k to be greater than 4. So if k is greater than 4, that'll be shifted up farther. Okay? When k is 4, we're going to have 2 roots. Until when? What about when k is 3? This will be shifted down farther. Then we're going to have 3 roots, right? So we're going to have 2 roots when k is equal to 4. All right, but as soon as k gets littler than 4, we'll be shifted less. So now it's going to be down. Right, Lainey? So it's going to be shifted down. And then we're going to have, till when? I think you're right, but how do you get that? You put not a 2 in for x, but put a 0 in for x, right? So let's put a 0 in for x. 0 minus 0 plus k. Oh, we just get k. So when k equals 0, this point is going to be right here. And we will have 1, 2 roots. So we'll have 2 roots when k is a 4 or a 0. If k is in between there, right, then we're going to have 3 roots. And so what about, I'm not quite done with 1 root then. What happens when k is less than 0? What about when k is less than 0? Well, I'll be back to 1 root. So, there you go. So when k is less than 0 or greater than 4, we're going to be 1 root. It'll be shifted up too far or down too far to have any more. When k is exactly 0 or 4, we'll have 2 roots. And when k is between 0 and 4, we'll have 3 roots. That's what it asks, right? When we'll have 1 root, when we'll have 2 roots, when we'll have 3 roots. Okay? So that was a tough one. That was a tough one. But if you think about it, it really needed no more knowledge than local max mins. How do you find it? You do f prime, set it equal to 0. And we need to have knowledge about shifting, vertical shifting. Really, that's all you need. And and then you had to be able to think that through. All right, 54. What was the problem? They gave you a position function. What is it? And they said t is positive because t is time. All right, this is your first look at a problem you'll see many times. Does it say a particle on the x-axis? Yeah. Okay. These are classic local max-min problems. These are number line graph problems, just like 19, 20, 21. Okay? But they have context. They're velocity, right? And so we've talked about position, velocity, acceleration, have that connection, position, velocity, acceleration. Here we're calling this function x. This is interesting. X is the output. Yeah. Because what we have, pretend there was an x-axis down here on the floor. This is like the Bismarck, North Dakota. East is positive, west is negative. That's what we got. We got a number line on the floor. We use number lines because that gives us positives this way, negatives this way, okay? So I'm standing at 0. If I'm going this way, my position's positive over here. My position's negative over there. But if I'm going this direction, my velocity is positive, right? If I'm going left, my velocity is negative, right? That's that whole Bismarck, North Dakota stuff when we first learned about derivatives. So this is x and this is x prime. So the reason we use x as our output is because this is an x-axis. This is just a number line. We call it the x-axis. So my position over here, so if I ask you for x of 2, what am I asking for? Your position at 2 seconds. Let's say it's seconds. So it's what is your position on the x-axis at 2 seconds? Your input is time. Your output is your position on the x-axis, just horizontal position. All right, so our velocity would be x prime. So what does it ask? When is the particle moving left? That'd be like the Bismarck, when is it moving west? When is the car moving west? Well, when its velocity is what? Negative. We want to know when the velocity is negative. Okay? Because what we say is its position is decreasing. This is really a chart question. X is decreasing when x prime is negative. Because think about it. What's my position? If I'm out here on the number line, I'm out here at 20. And now I'm at 19, 18, 17, 16. What's my position doing? 20, 19. That's decreasing. My position is decreasing. My velocity is negative. Now let's get over here. I'm at -1, -2, -3, -4. Isn't that also decreasing? Right? Negative and getting more negative. Positive and getting less positive. Negative getting more negative. My position, when I'm going left, my position is decreasing. Okay? So it's a chart thing. So when am I moving left is when my velocity is negative. An x prime number line would be a wonderful thing to do to answer this question. So I'm going to do the derivative. And that's 15t to the 4th minus 75t squared plus 60. And I'm going to set that equal to 0. Because if I'm going to do a number line, I want to know when it's 0, and in between I can see when it's negative and positive. See what I'm doing? So this is just like a local max-min problem, but it's got context to it. All right, so here's my velocity. So I can, oh man, let's see. This is let's take out a 15, yeah. Let's take out a 15. That'll make that much easier. T to the 4th minus 5t squared plus 4 equals 0. Right? So what do I got? This would be t squared and t squared minus 4 minus 1. Right? That'd give me minus 5t squared in the middle. -4 times -1 give me positive 4. Now both of those break down too, don't they? That'd be t plus 2, t minus 2, t plus 1, t minus 1. So 15, of course, would never equal 0. So t equals what? Plus or minus 2, plus or minus 1? What do we say about t? T's got to be positive, right? Because t's time, right? So that's a pretty common situation. So we're only going to do the 1 and the 2. We won't do the negative. So when t is 1 and t is 2. Now, what's that tell me about the particle? Now, what we got is we got a particle. Let's imagine this now. I'm the particle, and I'm on the x-axis. And I go here for a while, and then I turn around, and I go here for a while, and then I turn around, and then I get dizzy and fall down. And what do I got? What is it? What did I just find out with 1 and 2? That's when it stopped, right? Turns around. Well, maybe turns around. I walk this way for a while, and I stop, and then I keep going, right? I might not stop. All right, excuse me, I might not turn around. This is when I stop. Why? Because this is velocity equals 0, right? So we just found out when the velocity is 0. When's the particle stop? If it's going to turn around, that's when it's going to happen, right? When the velocity is 0. What happens? What would that be that we've already learned about with graphs if I walk and stop and they kept going? That's a flat spot, right? Graphically, that would be a flat spot, right? Increasing, kept increasing. Going right, kept going right. Be a flat spot situation. But we'll tell when we get to our number line. So let's put a number in here like 0. Let's put a number in here like 1.5. Let's put a number here like 3. And I might say, wait, t is supposed to be greater than 0. We can still put a 0 in, I think. But we could put a 0.5 if you wanted to. Maybe that'd be smart. Let's put a 0.5 there instead. Okay, now we got to plug that into where? X prime. That's why I labeled this. Now we can plug it into a lot of different versions here. I would say let's plug it into this one. Oh, now heck, let's plug it into this box. Then we don't have to square anything. Well, I'm looking at that 1.5 and I have to square it, and that might be messy. This is all no calculus. Let's put in a 0.5. 0.5 plus 2. Well, positive, right? 0.5 minus 2. Negative. So far I got positive times negative, right? Negative. 0.5 plus 1. Positive. So everything's still negative, right? 0.5 minus 1. Negative. So I had 2 negatives there, right? So what's that mean? That makes positive. Okay, now let's put 1.5 in there. Got a positive. 1.5 minus 2. Negative. 1.5 plus 1. Positive. 1.5 minus 1. Positive. So what I have? 1 negative. I have 1 negative. Okay, let's put a 3 in here. Positive, positive, 3 minus 2, positive, positive, 3 minus 1, positive. Everything's positive. When is this particle? So what's this particle doing? Right, left, right. So the question, when's the particle go left? Between 1 and 2. So it'd be, this kind of thing. 1 to 2. Right there. Right? Between 1 and 2. But I mean, look at that. That is just a local max min problem. There'd be a local max at 1, a local min at 2, which means he's farthest right at 1. That's a max. The farthest right or east he is. Local min at 2 is the farthest left he is. Right? In that little area. Now he goes back to the right, so it's right, left, and then right forever. Right? Because it'll never be 0 again. Okay? So that's how you can take this concept of local max min and you can put it into a setting here of velocity and stuff. Yes. So from 1 to 2 answers the question. Okay? So whenever you see that, here's a particle with a position, or here's a position function. When's it moving left? When's it moving right? That's its velocity. When's its velocity, positive or negative? Its velocity is the derivative. When's the derivative positive, negative? Is what you do when you do a number line graph. You find out when the derivative is 0, and then you check in between to see when it's positive, negative. It's hard to tell when a function is positive or negative, right? I mean, you can just start plugging in numbers and see if you get positive, negatives. The key is you got to know when it stops being one and starts being the other, and that's at 0. So whenever it asks when a function is positive or negative, you always want to find when that function is 0 first. And then do your number line to check when it's positive. Question?
Yeah, you said that it goes starts going right and goes
Uh-huh.
So can it also be positive between 1 and 2?
No, okay. Great question. You're confusing its velocity with its position.
Oh.
Yes, the particle can be positive position-wise and going right. It can also be positive position-wise and going left. Yeah, so we don't know where it is. That's a great question. We have no idea without plugging into this original. If we want to know where it is at 0.5 or 1, we'd have to plug into the original. That tells us where it is. Yeah, this is only about direction. Only about direction. We don't know where it's at on the number line. Yes, good question. Just direction. Same thing when we do a local max min. We don't know where those points are. We just know when it changes from increasing to decreasing, when it changes from the other. But we don't know where that is. Right. And usually we don't care. I mean, you know, later we'll do some problems where we might care, but later this week, but where we'll talk about what the actual outputs are, but not for this quiz, not right now. Okay? All right. So that's some good review right there. And we'll get in, like I said, for an hour tomorrow, we'll have time to get into some more review. Could you have a problem like this? Yeah, potentially. I mean, this early on, I'm probably more concerned that you can just do this process. So I'm probably just going to ask you about, you know, like 19, 20, 21. You know, here's a function, find the local max min, find where it's increasing, decreasing. This is the same process, same exact process. Okay. All right. Let's go ahead and then put aside most of that. I mean, does that answer pretty much everything? I mean, we'll have time tomorrow. If there are some other questions, or you might want to come in if there's some other questions in these sections that you still weren't sure about. The whole antiderivative thing, like 33 and 34, 32, why don't we just comment on those real quick. If you're really struggling with that, is not really a big part of the quiz, so I'm not really concerned about that part. But these should have been much easier. If you thought they were hard, you probably just made them too hard. What did we do? 32, 33, 34? 31 even. Okay, is big G an antiderivative of little g? How do you check if something's an antiderivative? Just do the derivative. So if big G is an antiderivative of this, that means when you do the derivative of this, you get 3x squared. So the answer? No, it is not an antiderivative. Yes. You could have done our rule that we said you could raise the power up to a 3, divide by 3, plus some constant. So you'd have 1/3 x cubed plus some constant. And you look at this, oh, no, it's missing the 1/3. So yes, that still could have been the answer no. Say, that your work would be your justification. So if you do the derivative, or like he did the antiderivative, and there's not a match, that would be your justification. Okay, so same thing is true here. Now remember, this is x to the 3/2 right here, right? Square root is half power. So this would be x to the 3/2. So we do the derivative, bring that down in front, it cancels the 2/3. And then you drop it by 1, that'd be x to the 1/2. The derivative for would be 0, so x to the 1/2 is square root of x. So this one is true. That one is an antiderivative. Okay? They got tricky here then. Big G is this, and big G prime equals little g. What's that mean? All that means is that big G is the antiderivative of little g. If you were going to put, remember when we did our, oh, I can't write on this. Sorry, those people watching the video at home. When we did this, right, big G, G, G prime, G double prime, right? Big G is the antiderivative. What's that mean? That means big G prime is equal to G. Big G prime equals little g, telling you, that's just a way of telling you that big G is the antiderivative. So they say find 3 antiderivatives of little g. Well, they gave you one, it's right there. What would be another one? Plus 1, plus 2, plus 7, whatever your favorite number is. That's all you had to do. They were just seeing, do you understand what this notation is telling you? Okay? So it was a really simple problem. And then this is very similar too. Big F prime equals big G prime. So that means big F and big G are both antiderivatives. Okay, is it possible that big G is equal to big F plus X? Well, again, do like we said up here, just do the derivative. What's the derivative of this side? Big G prime. What's the derivative of this side? Big F prime plus, what's the derivative of X? Derivative of X is 1, right? Right? So can that be true? They said big F and big F prime, big G prime are equal. Are those equal? No, so it can't be. What could be, if this was a K, if this was just some constant, or a C, then it could be. Because then the derivative of each of these would be just big F prime, big G prime. Remember what we said is the antiderivatives are only different by a constant. They're only different by a vertical shift. Well, these aren't. These are different by an X value. So, okay, so that is no. So those are just some questions about it. Again, that's not going to be, we talked about antiderivatives a little bit, but that's really not going to be an issue on this quiz. Next quiz, when we have time to talk about it a little more, we'll spend some more time on it. So don't worry about the antiderivatives really for right now. All right, let's talk about a few new things then. These are things that will not be on the next quiz. But we want to spend some time with them. Basically, let's, maybe in your notes, maybe on a new sheet of your notes, it might be a good idea to start kind of a derivative list. Okay, it might be a good idea to start kind of a derivative list of derivative rules. Okay, now we have some already. The very first one we learned was the derivative of sine x. Was what? Cosine x. Yes. Yes. I mean, I'll be honest, this may not be the only derivative list you ever make. You know what I mean? So if you want to leave space to add more to it later, you could. This is our list for right now. Okay? But yeah, you could leave some space, and it'll get kind of messy, and then at some point you'll probably want to redo it a little bit. And to be honest, once we get them all kind of figured out, then I'll have a PDF version of one that you can have as well. And then we also learned that the derivative of e to the x was e to the x. So those kind of fit in here. And then we learned this power rule, that if we have x to the n power, then we bring the n down in front. Right? That kind of thing. Let's see, what else did we learn? We learned some shifting stuff. We learned that how can I write this? We learned that if you're just going to do a shift of a function, that the derivative, that you'll just do the normal derivative and you'll still have that shift. Remember that? Like, for an example, let's do an example right below that. So if I had sine of x plus 2, the derivative of that is cosine x plus 2. Right? That's just my example. Or if we had x plus 2 to the 5th power. If we had x plus 2 to the 5th power, what would your derivative be? To the 5th power? 5 x plus 2 to the 4th power, right? So if you had x plus 2 to the 5th power, you bring the 5 down in front, drop it to the 4th, you leave the x plus 2 right down. All right? We also had a rule that said if you have a number multiplied on the outside of a function, we never really wrote it this way, but if you had 2 sine x What's that derivative? 2 cosine x. Because that 2 stretches the graph, which is going to stretch the slopes. So basically what that tells you is that that'll be k times f prime. In other words, if you got a k multiplied on the outside, then you've got that k will just be on the outside of the derivative too. So you just do your normal derivative.
It's just another way of doing that.
This is just another way of writing the rules that we kind of all going to do. Okay? So it's just not a huge. The last one I would want to put up here would be, and we haven't done too many of these. Okay? And these, like I said, these ones I'll put here, we talked about them a little bit. They're not really a big emphasis for our quiz, so we don't have to worry too much about them here. But what did we say if you had a k multiplied on the inside? Say it again. Has to also be moved to the, remember we said kick it out? Because what's that do? It squeezes the graph or stretches it. So if it squeezes the graph, it makes everything steeper by a k factor. And it moves in where they are. So, and we remember when I said the inside always stays the same? So the inside of any function always stays the same. Look what happened here. X plus or minus h, you're still going to have x plus or minus h inside. So what happens here is we have to kick a k to the outside and we leave the k on the inside as well. So when we have a k on the inside, we do our normal derivative. The k stays on the inside. We have to kick out a k. So if you had sine 2x, the derivative, to cosine 2x. Let's just write that down. So if you, an example here would be if you had sine 2x and you were going to do the derivative, it's 2 cosine 2x, right? Because that 2 squeezes it in, so it's going to double all the slopes. So you have to kick that 2 on the outside. Okay? So those are ones we have so far. And I'm kind of out of space, so I'm going to go to the next page for them. So that's kind of what we've talked about with slope so far, or derivative rules so far. All right. Now, the book jumps around here a little bit. Section 2.5 is about something called differential equations. We're going to hold off on that until after the quiz, because that is really new and different, and so I don't want to throw that out before the quiz. So we're going to come back to that. Differential equations. It kind of deals with antiderivatives. Okay, and differential equations is something your book kind of comes back to every once in a while as we learn new stuff and we can apply it. Same thing it does with parametric equations, the line and the ranger thing that we're still going to come back to as well. Okay, so those are things we delve into and then we gradually learn about them as we go. So that's 2.5, so we're going to skip that for right now. 2.6 is about exponential functions like e to the x. And 2.7 is about trig functions. So what we're going to do is we already got an e to the x rule, and we've already got a sine of x rule. What we're going to do in section 6 and 7 is we're going to learn more about the other exponential type functions. We're going to talk about the log function, and we're going to talk about the other trig function, and get the rules for those. And then the homework problems are really mostly, the ones we're going to do today, are just about stuff we've been talking about. Do the derivative, here's your new rules, now do the derivative, practice doing those, and also give you some like local max min kind of problems. Where's the function increasing? So stuff that is like on the quiz. The only difference is on the quiz, I'm going to give you like polynomials, like what we've been doing, like x to the 5th and x to the 4th, those kind of things. Okay? Our next quiz will have some of those same questions, but we'll have e to the x's and sines and cosines and stuff. Okay? So we'll just start that process today. So it isn't anything terribly out of the what we've been working on. So here's the first one. So we already have e to the x. Now we're going to talk about just any base to the x. All right? Talk about any base. And you know what? To be honest, since it's a base, can we change that b to an a? Sorry. I know I always do that to you guys, but that's pretty easy. Change that b to an a, or that a to a b, excuse me. A to a b. This will be right in your derivative. Yeah, this can be right in your derivative. So if you want to make a a note that these are the new ones, you know, now that's fine. But since B stands for base, let's use B. I think that's what your book uses too. Now you might guess, so an example here would be like 2 to the x, right? That's what we're talking about. 3 to the x, 4 to the x, whatever. Well, you might guess it might be what? Oh, yeah, I didn't think about that. Of course you would think of that. I guess I was thinking that this is more like e to the x. Is this more like e to the x, or is this more like x squared? This is more like e to the x. We do not bring the x down. No, we never bring the x down. We do that on logs maybe, but that's a whole different thing. Here, let's go back to this. Did we bring the x down here? No. When we have x raised to a number, that is the power rule. We do not do it with exponential functions. They are different. So if the derivative of, so here's what I was getting at. If the derivative of e to the x is e to the x, a good guess might be that the derivative of 2 to the x is 2 to the x. Well, it turns out you're almost right. It turns out you have to tack on a multiplier, which is natural log of 2. You have to multiply it by natural log of 2. Now, if somebody has their calculator handy, do ln2 for me on your calculator and hit Control Enter, which will give you a decimal. Type in ln2. How much? 0.69. Okay, and here, let me tell you what's happening. Because 2 to the x looks just like e to the x, it just doesn't go up quite as steep. And so what happens is the derivatives are not, the slopes are not the same as the y values, but they're close. The y values multiplied by 0.69 whatever, right? ln2 is just a number now, right? That's different ln x. ln x is a function. ln2 is just a number, okay? All right, so the rule is the derivative of b to the x is b to the x times the natural log of whatever the base, whatever the base is. So if this would have been 3 to the x, the derivative would be 3 to the x times ln3. If it was 4 to the x, it'd be 4 to the x times ln4, and so forth and so on. You know what? It kind of makes sense, because this one, don't write this down, but technically this one follows the same rule. This is e to the x times ln e. What's ln e? Right? So actually e to the x follows that same rule. It's just we don't write it because ln e is just 1. Okay? So that is the derivative rule for any exponential. All right? An exponential is when you have x up in the power and a number in the base. All right, now let's do the logs. We haven't talked about log rules at all. Natural log of x. The derivative is kind of interesting. 1 over x. It's kind of funny because sine x, the derivative of cosine x, and exponentials, the derivative is an exponential. And in power rules, the derivative is another power. It seems like they stay within the same family. Whenever you do the derivative of trig, you get another trig. You do an exponential, you get another exponential. Mostly that's true. This is the one exception. Natural log of x, the derivative is just that. 1 over x. And a strange. Just have to memorize that. Now, an offshoot of that is the log of any other base. Log base b of x. The derivative is 1 over x times 1 over ln of the base. It's very similar to the rule for exponential. So if you have a different base of a log, it's still the same derivative. It's still 1 over x. But then you have to tack on this multiplier, just like you had to here. But it's 1 over lnb. So that means if you had so what's the derivative of log base 3? If you had log base 3 of x, the derivative would be 1 over x, 1 over natural log of 3. That would be the derivative. 1 over x times 1 over natural log of 3. Now you could put those together as one fraction if you want to. You could have 1 over x ln 3 if you want. Okay? And again, this one actually fits that as well, because what would this be? This would, because natural log is base e, so this would be 1 over ln e, which is just 1. Right? So natural log does fit this. This is the generic, or the just for any log. All right? That's the derivative. So I'm going to separate these a little bit. You don't really have to, but now we're going to get into the trig ones. So that's basically the do stuff in section 2.6. Is those two rules, three. Okay? So what that means is now if you want to do a local max min problem or something like that, you can now do the derivative, you can set it equal to 0, you can work with it. Right? You can do the stuff that we've been doing in the other ones with those derivatives. Same stuff. Okay, now section 2.7 talks about trig functions. So we already know about sine and cosine. So let's write the other ones. Or excuse me, we already know the derivative of sine is cosine. So let's do the other 5 trig functions. Well, actually, we're only going to do, yeah, we'll do all of them. I'm not going to probably ask you about most, but a lot of them. Okay, I'll show you the ones we'll focus on. All right, derivative of cosine is negative sine, turns out. Now remember, when we did the derivative of sine, we looked at it, we said we plotted its slopes, and we said the slopes start at 1, but they get less towards 0, and then they go negative, and then we said, hey, that's what cosine is. Well, if you think about the slopes of cosine, what do the cosine slopes do? They start at 0 and go negative right away to -1, and then they get less negative. Well, if you plotted that, start at 0 and go negative right away, and then get less negative, what do you get? Oh, you get negative sine. You get the sine graph flipped over. Okay? So the derivative of cosine is negative sine. The derivative of tangent x is secant squared x. Just have to memorize. Derivative of tangent x is secant squared x. Now, we're probably not going to get into much with these. Sine and cosine will be the big ones that we'll want to know. You know, derivative of tangent is secant squared, and I usually pair these this way because they're related. Cotangent is very similar. It's negative cosecant squared of x. So if you can remember that the derivative of tangent is secant squared x, then it's not too hard to remember the derivative of cotangent is negative cosecant squared. Notice the co-functions are all negative. Sine was cosine, and cosine was negative sine. So cosine is negative, cotangent is negative, and cosecant is going to be negative. You'll see in a minute. All right, so that leaves us just 2 to go. The derivative of secant x is secant x tangent x. Secant times tangent. And that leaves us cosecant as the last one. You can probably guess it. We got a guess? Negative cosecant cotangent. Again, very similar to what secant. Secant derivative is secant x times tangent x. Cosecant is negative cosecant x times cotangent. Now again, those are ones that we won't run into a whole lot, especially for this, well, this quiz we won't run into them at all. And then our next quiz, which may come before Thanksgiving, so we may, have quizzes here just about a week apart. Then we'll get into these a little more. Okay. but it's really just about memorizing. But for right now, focus will mostly be just on the sine, cosine, a little bit with these rules here. All right, so let's look at a little bit on the homework here. Let's start at page 139. On your assignment sheet, now, this is basically your assignment for tomorrow. We probably won't take time to go over it and work on it, or answer questions about it. We'll probably do that after the quiz, so that would be something we might do on at the end of the period on Wednesday if we have time, or on Thursday first thing. But you'll have another assignment after the quiz on Wednesday. Okay, so how much we get to go over, we'll see. But you should probably work on it for tomorrow. Although if you want to go back and be reviewing for quiz and doing that kind of stuff, you can. Now we're going to be talking about some of those things on Tuesday as well. So you'll have that opportunity to do that deal. But right below the line it says 2.4. Right? Everybody see that on the assignment sheet? Where it says 2.4? You've got those lines that say 2.6 and 2.7. They're kind of grouped together there. Those are the two lines we want to look at. Yeah. Okay, these two lines right here, 2.6, 2.7. Okay, so 2.6 is the exponential stuff. 2.7 is the trig stuff. All right, so let's just pick one out of each to get ourselves started here. So, number 6. I think our best use of time at this point maybe would be just to kind of work together here a little bit on this. So, page 138, 139. I'll do part of it here with you. Okay, so this is on page 138, actually. It says use theorem 12, which is just the rule. If you look back at theorem 12, it's just the rule that we wrote down. It's a derivative rule for logs. Okay, is all it is. To find h prime of 1/10, h prime of 1, h prime of 10, h prime of 100. Okay, well, how do you find h prime of anything? Well, one way is to find h prime of x first. So all this question is asking is you to use your rule to find h prime of x. And so what did the rule say? What is a derivative of this? 1 over x. 1 over natural log of 10. Right? The base. So 1 over x times 1 over natural log of 10. That is the derivative. Of x, h prime of x. So what's h prime of 1/10? Plug in a 1/10 in for x. Now what's 1 divided by 1/10? That's just 10. So this would be 10 times 1 over ln 10, and probably a better way to write that would be 10 over ln 10. Right? Now I don't care. If you want to leave it like this, I'm fine with that. If If you want to write it like that, that's okay too. What about h prime of 10? Well, no. We put a 10 in for x. So that'd be 1 over 10 times 1 over natural log of 10, right? Which you could just leave, or you could write 1 over 10 ln 10. Right? Either way there, I'm fine. So it's really nothing more than doing the rule and then plugging in those values in. Because h prime of 10 means find h prime of x and then plug a 10 in. Okay, right here, right there. Okay? All right, so 8 is very similar. So let's jump ahead. I'm sorry if you like to have your homework all nice and neat and tidy. But let's jump ahead to page 147. Now, here is where we begin in section 2.7, the process of having to know your trig functions and your trig values. Okay? Because on number 10 through 13, they give you this function, and this would be a no calculator problem.
Do we have a
Yeah, good question. You know, on this quiz coming up, your calculators are basically for the tables. You know, we did the limit tables. That's about it. That's about all we use the calculators for. Okay? So it'll be a fairly short calculator section again. Okay, so they give us this function in the interval -5 to 5. Okay, for x. Does G have any? Oh, they called it G. Sorry, that's G of x, not F. G of x. Okay. I mean, it's not a big deal, but I mean, we should use it. All right. So G of x is that. Does G have any stationary points in I? I is the interval -5 to 5. If so, where? Does G have any inflection points? If so, where? Does G have any local max? If so, does G have any local min? So you see what I mean? It's the same thing, except inflection points are kind of new. So let's just go through 10. Does G have any stationary points? Where do you look for stationary points? No. Where G prime equals 0. So we do G prime, which would be 1 plus cosine x, and we would set that equal to 0, right? This is just like 19, 20, 21, this local max min stuff we've been doing, except it's got a cosine in it, okay? So we got to solve that. So we subtract 1 from both sides. Where does cosine x equal -1? So if you're a unit circle kind of guy or gal, cosine is the x. Where does it equal -1? That'd be at pi. But now wait a minute, we got to go from -5 to 5. So couldn't it be -pi, which means you go back this way? Because that'd be -3.14, so that'd be in that interval. What else? If you went around again, that'd be 2 pi, that'd be 3 pi. That's like 9 something, right? So now we're out of the interval. So I think it's those two right there. Now, here's where just thinking of the cosine curve could be helpful as well. Right? Or excuse me, just think of the cosine curve. Where does cosine equal -1? Right there and right there. At -pi and at pi. Right? So that'd be could be useful as well to get that. All right. Now what do we do with that? Those are our stationary points. Come on now, what do we do in 19, 20, 21? Well, we're done with 10.
Yeah.
Yeah, I'm sorry, we're done with 10. Where are the stationary points? There they are. But now, let's skip 11. Just forget 11. Don't even do 11. Okay? I mean, we will, but just don't do it for right now. So 12 and 13 want to know about local max and min. Think problem 19, 20. Think about the velocity one we did with the particle.
So you got two of them.
Number line. We need a G prime number line is what we need. With our stationary points put on there. Negative pi and pi. Now we got to pick numbers in between. So 0 would go here. Now wait a minute. Where are we going to plug these? We're going to plug it into G prime. So we better pick numbers. Somebody said 5. Do I want to do cosine of 5 without a calculator? No, I'd rather do numbers that I could that I know, right? So what's a number bigger than pi? How about 2 pi? How about negative 2 pi? That's not in the interval though. Yeah, that's not in the interval.
So we can't use
How about what would be bigger than pi? How about 3 pi over 2? 3 pi over 2 would be bigger than pi. And how about negative 3 pi over 2? Those have a better chance of being in there. That's like 4.7 something. Okay? And we got to plug those into there, into this G prime. So what's 0? Let's do 0 first. What's cosine of 0? 1. 1 plus 1? 2. So that's positive. Let's do 3 pi halves. What's cosine of 3 pi halves? Isn't that 0? Cosine of 3 pi halves is right here. That's 0. 1 plus 0? One plus 0? Positive. Let's put in negative 3 pi halves. Oh, that negative 3 pi halves is still 0. Right? Negative 3 pi halves is right over here on the cosine graph. 1 plus 0 is, oh, what's that tell you? Those are flat spots, aren't they? So, does G have any local max? No. Any local min? No, right? These would have had to switch positive to negative, negative to positive. Well, it turns out if you went cheat, get your calculator out and graph x plus sine x, that's exactly what it looks like. It just kind of keeps going like this. It hits a flat spot and then it goes up. And then it hits a flat spot and it goes up. And it hits a flat spot and it goes up. And it just kind of keeps doing that. Okay? But our number line told us that's what's happening. So there aren't any local, but you see, that's the same kind of problem we're doing. But now we're doing with a trig function instead of a polynomial function. Yes? No, well, okay, because those are flat spots, but there are also other inflection points, because think about it, you have a flat spot, it's concave down, then it goes to concave up, so as it's going up, it switches to concave up, but then it switches to concave down to get to the next flat spot, so there's another one in between there too. To do the inflection points, you'd have to do the second derivative and set it equal to 0. And then you start getting into some other, and so let's
So are we gonna do that?
we will, but you don't have to right now. You don't have to right now. We will before our next quiz, but yeah, so we will do that for sure, but I wouldn't worry about it right now. Okay, so the rest of the homework there is mostly just the derivative rules. They're just problems where they say do the first derivative, and then they say do the second derivative, and then I think some of them say even do the antiderivative. So just try to do it backwards. So it's just getting you comfortable with the rule. So do that, but also be getting ready for our quiz on Wednesday as well.
I can't do it later tonight.
There aren't any real good review problems at the end of this chapter, so it's going to be more about going back over our
So you
old
just come tonight?
stuff.
Is there